You might notice that we jump right from chapter 5 to chapter 7. Um, well, that's because chapters 5 and 7 are about computing integrals, and chapters 6 and 8 are about using integrals. And so the way I'm structuring this course is that we figure out first how to do all the integrals, and then in the second half of the quarter we'll use them to do different things. Anyway, chapter 7, section 1 is integration by parts. As with so many other integration techniques, what we're trying to do is we're trying to run derivative rules backwards. We're trying to take antiderivatives. And integration by parts is going to be the product rule backwards. So let's start by looking at the product rule. The product rule says you're taking the derivative of a product, u times v. In fact, I'm not going to use parentheses. I'm just going to say duv. And I'm taking the derivative with respect to x. So I'm thinking of both u as a function of x and v as a function of x. The product is a bigger function of x, and the derivative of this big function, this product, is the first function times the derivative of the second, so u dv dx, plus the second function times the derivative of the first, v du dx. I just love saying that out loud here. duv dx equals u dv dx plus v du dx. It just kind of rolls off your tongue. Okay. So now I'm going to rearrange this a little bit and see if I can turn it into some antiderivative formula or some integral formula. And so the way I'm going to do this is I'm going to take this v du dx and bring it over to the other side here. And I'm going to reverse the sides. So this is coming over here. So I've got d uv dx minus v du dx. And that's equal to this thing that's left by itself, u dv dx. Okay. So this is just the product rule, but I've rearranged things a little bit. Now I'm going to integrate both sides of this with respect to x. So the integral of u dv dx times dx equals the integral of duv dx. And I'm using a property of integrals here in that the integral of this difference is the difference of the two integrals. So I can do these individually. V du dx. Okay. Now, there's several things that happen here. First of all, in this first integral and the last integral, this is just like what we do with the u substitution, that this duv dx, sorry, dv dx times dx, this right here, essentially the dx's cancel out, and this is just the integral of u dv. Right? If v is a function of x, then the differential dv is the derivative of v times dx, and that's exactly what this is here. I'm just taking the derivative, sorry, the differential v is equal to this derivative times dx. Okay, that's what we do with u substitutions from section 5.5. Right, and likewise, this last integral here with this du dx times dx, that's just the integral. So there's a v here. That's just now a du. Okay. So u dv equals something minus v du, and this something is the antiderivative with respect to x of the derivative with respect to x of u times v. Okay, so let's see if we get this straight. You take the derivative of u times v with respect to x, and then you take the antiderivative of that. Well, shouldn't you get back to where you started from? Well, quite possibly. The only reason you wouldn't get back to where you started from is if you had a different constant that's being added on. I'm not going to worry about the plus c right here, because the plus c will also show up on this one, and then we'd add the two constants together. Okay? But this right here is the integral with respect to x of the derivative with respect to x of u times v, so you just get back to u times v. This right here, this equation is what we call integration by parts, or where I come from, integration by parts. Okay. Let me show you an example. Essentially, you've got an integral of something times the derivative of something else. And we end up with another integral, but hopefully this integral will be easier to do than the one that we started with. So here's my first example. How about something like the integral of x times the sine x, okay, dx. Now I'm going to see if I can recognize this in this form. I need a u times a v. So I'm starting off with a u and a dv. So I have some choices, and this is the case with integration by parts. You've got a lot of choices, and some of the choices may not work so well for you, and some of them may work better for you, and you don't necessarily know ahead of time. Practice is going to make you better at doing this, but in any one of these problems, I set them all up the same. I have u, du, v, and dv. I start off always with u and dv, and then I got to figure out what v and du are. Okay, so I'm going to, on this one, I'm going to guess right the first time just so that it goes quicker. I'll guess wrong on another one to show you what happens. Anyway, I'm going to let u be x and dv be everything else, sine x dx. That is, this whole integral has to be made up of u and v. So everything that I see is going to be either accounted for in the u or in the dv. Then I'm going to take a derivative here. If u is x, then du is dx. And backing up here, I arrange these the same all the time, even though I know I start with u and dv, and some people put those on this level, and then they write du and v underneath. I do it this way just so that I keep track of the u. I'm taking a derivative to get what du is, but the dv I'm taking an antiderivative to get the v. So just the up and downness on the page, to me, going down is taking derivatives, going up is doing integrals. Anyway, it keeps me a little straighter, less likely to you know, if I take an antiderivative of x, it's going to be x squared over 2. If I take a derivative of sine x, it's going to be positive cosine x, but the antiderivative would be negative cosine x. And I don't worry about any plus c's at this stage. I'll worry about them at the end when I do this last integral. Okay. So anyway, I've broken it up into the u, that was this part, and the dv was everything else. Okay. And then I figure out what du is, I figure out what v is, and now I'm just going to use that formula. So this integral should equal u times v. So this one times that one. So x times negative cosine x minus the integral of v times du, right? V times du. So v is negative cosine x, and du in this case is just dx. And I look at that new integral and say, hey, that's a whole lot nicer than the other one was. This was x times sine x. The x went away here. And so now I've just got a cosine x. And it's like, I can integrate that. And actually, and the minus minus is going to become a plus here. So this is minus x cosine x plus, and the antiderivative of cosine x is positive sine x. Now, I'll throw in the plus c. I started off with u times dv. This was the u. This was the dv. I ended up with u times v minus the integral, and this right here is what the integral, actually that whole thing was the integral of v times du. Let's do another example. Here's example number 2. Just off to the side here, I'm gonna write this down just so I have it. The integral of u dv equals u times v minus the integral of v du. Okay. After you do this enough times, you don't have to write it down to remember each time, but anyway, to start with, we may need that over there. So I'm going to look at an integral here of x squared times e to the x dx. Okay. Now, generally, integration by parts problems jump out at me because they're essentially a product of two things, right? We have rules for integrals saying you can do the integral of a sum by the sum of the integrals, but it's not so with products, right? The product rule wasn't the derivative of a product as a product of the derivatives. No, it didn't work that way. You had this more complicated product rule, and so hence we're going to have a more complicated rule for integrating products. Now, granted, u substitutions were also dealing with products of a couple of things. For instance, on this problem, if this was an x down here and this was an x squared up there, I'd do a u substitution. But it's the other way around here, that the derivative of this x is not that x squared. So anyway, I'm going to do integration by parts here. U du, v dv. In fact, on this one, I'm going to go the wrong way and show you what happens here. I'm going to let u be e to the x on this one, And so then everything else, the x squared dx has to be the dv. The derivative of e to the x here is just e to the x, so du is e to the x times dx. And the antiderivative of this x squared dx is x cubed over 3. So what I've got now, started with that, now u times v, so e to the x times x cubed over 3, minus the integral of v du, so that would be x cubed over 3 times e to the x dx. Okay. There's absolutely nothing wrong here. This is perfectly good work. The problem is that our integral, seems to me, just got more complicated. We started with an x squared times an exponential. Now I've got an x cubed times an exponential. It's like it's more complicated than it used to be. So it's true, this integral is equal to this, but this isn't helping me towards getting the right answer here, getting the value of the integral. So instead, let's try again here. Try again. I'm going to do this integral of x squared e to the x dx u du v dv. Kind of gives us an idea of what we're looking for too when we're making these assignments. If I, rather than putting the exponential here as u, let's put the polynomial piece. So let's put that x squared there, which means that the e to the x dx, everything else that's in that integral, it's got to be down here in the dv. Take the derivative here. This would be 2x times dx. Take the antiderivative. Well, e to the x is just as easy to integrate it as it is to differentiate. So trying it this way now, what would I have? I have the integral of u dv equals u times v minus the integral of v du. Okay, so u times v is x squared e to the x minus the integral of v du minus the integral of this times that. So 2x e to the x dx. Am I any better off than I was? Actually, I think I am, where before I had a quadratic times an exponential, now I just have a linear function times an exponential. Okay. And you can probably maybe guess what I'm going to do next. Oh, I think I'm going to integrate that by parts. So, actually, let's not put them equals yet. I'm looking at this thing. I have an option here. I can either take the 2 and put it out in front, or I can just leave the 2 in there and carry it along. I think I'm just going to leave it in there. So I've got a u, a du, a v, and a dv. So again, I'm going to do the polynomial piece here as the u, and the exponential piece as the dv. If I did these the other way around at this stage, what I would get is I would get something that canceled that out, and I'd end up with a new integral that equals the original integral. I'd be at a point where I'd said the integral of this thing is equal to itself, and it would be absolutely true, which would tell me that I didn't make any mistakes, but I didn't actually evaluate the integral. So once you've made the commitment to the polynomial piece in the u, stick with it on the next round. Okay. Here we go. How about taking the derivative? That would be 2 dx, and taking the antiderivative here, that would be e to the x. And I see I'm running short on time. So I've got an x squared e to the x minus, and this whole thing gets minused, u times v, 2x e to the x, minus the integral of v du, which is 2 e to the x dx. And hey, I can integrate that thing. So I've got x squared e to the x. I'm going to distribute the minus sign in at the same time. So minus 2x e to the x plus, and the integral of this thing is just 2 e to the x plus a constant. That one took 2 integration by parts, but I started with a quadratic, got to a linear, and then got to it with just a constant. Okay. We'll do some more in the next video.